let's start. So my name is George, or for all those people that are coming from Germany, Georg. I'm from the company Wandelbots. We are based in Dresden, and in the next minutes, I will show you what is our main domain. This is all about teaching robots from human interaction. And I will just talk about more about the application domain, not so much about the problem and the solution that we deliver. And so I will be much more superficial than the previous presentation, as you might be used to it for startups, right? So, however, we are going to help our users to teach robots without writing a line of code. And for this, we provide a certain software stack and physical input devices that you can use for this task. So, but when I'm talking about robots, I'm not talking about those humanoid things that you might have seen in the shopping malls or in hospitals or in elderly care, such as the Aldebaran Pepper or Now robot that now belongs to SoftBank. No, I'm talking about real industrial robots that are installed at the shop floor in manufacturing lines, and that can lift very heavy weight, that can do very accurate tasks, so less than 1 millimeter accuracy, that are very large and run very quick, and that are foremost universal manipulators, which means you can basically attach any tool that you can think of at a robot, and then let the robots do human tasks that were before not automated. So, and because those robots are very general purpose machines, they are also very difficult to program, because you do not only have to consider all the geometric and the trajectories that robots have to move, but also the physics and the kinematics of the robot, and then also all the parameters that come for the tool. Okay, and another thing is that when you have a stadium full of people, then you might find one robot engineer, and the statistics then says all the other people are no robotic engineers. That means the job market is very narrow, and this is a very difficult problem for small and medium-sized companies, because they don't find people themselves that can help them with automating their let's say manufacturing steps on the basis of robots, but they have to call for service agencies that do the job for them, and that they are very expensive, because of course also for them job market is quite competitive. So another problem is that those robot engineers use very old-fashioned conservative languages. So this is just a simple photo, of course, it shows PHP, but what they actually use is something like Pascal or basic dialects to write code and logic, and this is very hard to maintain, and it lacks of object orientation and, for instance, reactive programming and all the things that you might be used to when you are using, as an AI or ML engineer, maybe Python or so. So for this, to solve those pains of our customers, we developed a product which is a combination of hardware and software. Let's say 20% of it is hardware. It's the thing that you see here. It's a pen called a trace pen. And a trace pen is basically nothing else than a tracking device. So it's tracked like you have seen it maybe from your HTC Vive virtual reality goggles. There are sensors within the trace pen, and you can track them in space, not only the location of the trace pen, but also the orientation in space, which is very important in order to navigate the robot afterwards very well. And the software that we deliver translates the recorded motions from this trace pen to robot motion, which is the actual trick. So in principle, of course, recording three-dimensional data, when we're not talking about accuracy, is not so hard. The problem is then when you want to translate it to the certain robot that you have in place. And for this purpose, we have basically a product software engine that translates to different protocols, to all those vendor-specific robot languages, to the kinematics, to the different physics of all those robots. And yeah, and you support this by user interaction. So what you see here is an app that comes with our software. You can use it to fine-tune the kinematic points to which the robot shall go. and also conduct the logic that is beyond those motions. So logic is, for instance, controlled by IOs that are kind of electric signals that are coming to the robot, and the robot may also send signals in order to control a tool that is attached to the robot. So what you see here is a comparison between using our software on the right and using the traditional teach pendant, which is very specific to the robot and very difficult to use. So that's basically our product. And now you have two challenges that we solve within our stack. And this is, first of all, getting high quality data from the human, recording the trajectories, the three-dimensional ones, with the trace pen. So you have to remove arrows, shaking hands, and maybe losing contact to a workpiece with the trace pen, and all those input errors. And the other thing is intelligently translating the input to the robot. Those are the two things that we want to solve based on machine learned models and other techniques. So in general, you have, after using the trace pen, a record. This looks like, I don't know whether I can switch on the laser pointer here, maybe. Wait, let's try it. So you have this trajectory here, and the trajectory must be translated into a so-called skill. The skill is our programming model. It's nothing else than a kind of imperative logic. And in order to get there, the user basically manipulates the data that came from the trace pen. And this is a refinement or tuning step. And of course, if you know the application case, so for instance, if you know that the user wants to do welding with the robot, you can use the user feedback and learn it in order to automate the design steps from the recorded trajectory to the skill. And this automated or semi-automated design is also supported by our models. So we have 3 AI pillars at Wandelbots. The first one is generating motion from time series data. So basically we record with the trace pen the time series. The time series is multidimensional, and the parameters are taken into account in a model, and the model then predicts certain keyframes with a lot of parameters within the time series that are then translated to robotic commands. The second pillar is generate either logic from the machine learned application cases. That means when you get a time series and you have knowledge about what the user wanted to do, for instance, welding, then you know already what would be a template, for instance, for the process, and how can you predict the parameters of this template, which are manifold in terms of geometry, physics, acceleration, for instance, and certain control parameters that make sure that the robot moves the best way for the certain application cases. And the final thing, which is still future and R&D also in our company, is reacting to user interaction. So in the industrial robotic community, there exists a term which is called cobots. And a cobot is basically a robot that can sense, for instance, forces or at least any kind of user vicinity. So if the user, for instance, touches the robot, that is sensed, or when he's just close from an electrostatic field, and then the robot should react to that. And the reactions are, of course, very high variant, yes, and the robot has to learn how to react to a human interaction. This is another pillar that we always do research on. So I will mostly talk in the next few slides about the time series data. So what we have as the input is a record, the record from the trace pen. And the record comes with a lot of data. First of all, it's of course the time series, so every point within the record has a timestamp. And then each record entry, so to say, has a location. So the location is three-dimensional, three dimensions are X, Y, Z. And you have orientation. Orientation is mostly represented in either rotation matrix, or maybe in a quaternion, or Euler angles, which are not very much used because they have problems from representation perspective. So these are already many dimensions here, but what comes comes additionally is the application type. So if you can use the application type as an input parameter. So if you want to predict, for instance, which certain points of the trajectory should be taken into account when generate the motion, then you should know about the application type that is existing in that certain setup that you are currently teaching. What you have otherwise are interactions. So maybe you have seen it at the trace, and there are buttons, and when you press a button, then you want to have, for instance, a gripper opener or a gluing dispenser dispensing the glue. And all those things can, of course, also be correlated. And the final thing is the motion type. Motion type is a quite specific parameter for robotics, because it tells the robot to go, for instance, a completely, absolutely controlled straight line from one point to another, or it tells the robot to go the most fastest way from one point to another, or maybe go a perfect circle in a static, stable radius around some points. And this motion type can also be used in our models. So what you have here is basically a correlation between the record and the tuning that you make, that makes use of the record and sets up all those parameters. And the other one is the design correlation when it comes to the logic of the skill, so that you maybe say, before I'm moving along this piece, I'm predicting that the user should first activate a certain tooling or do a certain step within the template and, for instance, accelerate from a certain point to start of the trajectory, which would be the most smartest thing I can do in order to get all the operation right. And the user might be not knowing this beforehand, because users maybe the user is a robotic engineer or a software engineer, but not always the user is an expert in the application domain that shall be programmed with the robot. That is the thing that we help. So I've also shown you some slides from our actual app. What you see here on the left side is already the most compact way how to use our AI technology, our machine learned model. You basically get a time series data, which when you look very, very closely to your screen, you see that violet line here. This is the raw data that came from the trace bin, and the points on the line are the predicted keyframes. You call the keyframes are nothing else than waypoints, but the waypoints are, of course, with a lot of data, so we can also do, for instance, splines and so on, and they are predicted based on the application type. We use different ones. So, for instance, you might see that from this point, the white line is not completely straight. It's a bit bended because the algorithm predicted that the user actually wants to have a very large circle section motion here. So, and you can select with this very simple slider here how many keyframes, how much is the resolution of keyframes that should be predicted from our algorithm. So after using this first step, which you can speed up your conducting your first prototype of your process up to 30 seconds or so, you can also, of course, do all manual manipulations, which is much more complex. And you see here, all those steps are just for really, really intense fine tuning, and the user might be overwhelmed with it in the beginning. So just avoid it and just use maybe the predicted keyframes in the first step. After that, you get a screen where you can have those motions connected to a logic, to imperative logic, which you see here. This is just a sequence in this case, but you can also have, of course, branching like just in normal imperative language. And afterwards, you can move the robot, so in a kind of debugging mode from our software, or you can export code. In this case, it's the so-called UR script, which is the language of the universal robot that you see here in a virtual digital twin. Okay, what do we want? What do we want actually to achieve with all this? So, as I said at the beginning, robotic programming is very difficult because there are so many different vendors with different interfaces, different programming languages. Then we have the kinematics, the physics, the geometry, the different kinds of application cases. And because of this, there is a phenomenon that happens always even with normal visual programming languages, if you get to a certain point of complexity, the ease of use of using the tooling falls apart, because then you cannot avoid to learn all the other things that the robot also does, or also can do, and then you are basically out of the game if you don't invest 3 months or so of learning before you start with your first robotic application or programming anything. And for that reason, we want to get you to stretch this S line here with using the tracepen, first of all, in order to let the user programming complex motions for the robot very much easier. And the other thing is, and this is of course now a claim and an advertisement slide, that we do not want to have this S line, and we want to support the user with our intelligence system, with our ML-based model so much that you get just a very tiny degrees of ease of use with the ongoing complexity. So this is all of my presentation. There's just two additional slides about the company. We are now 100 people and existing since 2017. We are really a startup, so everything is in motion, like always. You see here many people. Currently, we are of course not so much at work because of the pandemic. But some people still need access to our robot. If you look here very precisely, you see some robots shining through the window. I have added this outline here of Germany. This is where Dresden is. There's Dresden in Eastern Germany, and that's me. As you see, I like arrows. And if you want to have contact besides this conference, of course, I'm staying here for the breakout session. You can talk about business cases, about applying yourself, or even visiting us, also to the people to talk to, or go to our website for first contact information. So now I'm done, and I'm ready for any questions that you might have. Thank you.
Thanks a lot, Georg. Really nice thing. I think you're opening here an industry which was, I think, a decade ago just for big players, right, in the industry, and I think it goes more long tail. Is that actually also your vision to go into the semi-professional market with that, or where do you position yourself then in the next years?
Well, the long-term vision of Wandelbots is to really be a platform in controlling any robot in the market, also having other contributors to our platform than ourselves, of course. And also a strong vision is, for instance, that what I said at the beginning, that in the SME market, it's very difficult to get a robot in-house and have also the knowledge to program it in-house. And so the whole setup is very expensive. And therefore, we want to help those people in order to get their robots activated on their own and empower them to use them based on our software, because our software eases the access to those machines.
Yeah, okay. Cool. Really nice. Yuri, do we have some questions already in the Q&A part?
No, we don't actually, but maybe I can bridge that once. Maybe there's some questions. So if in the audience anybody has a question, just drop it into Slido or also the chat here on the stage. That's fine as well. I still remember that you I said to Jan before that I remember you actually pitching for a TechCrunch Disrupt a couple of years ago. I think it was 17, and I was immediately intrigued by the presentation. It's like, this is actually a nice idea. I know it's super great that you kind of only 3 or 4 years later you actually have such a big team, and that's even a kind of an East German success story. So super happy, Georg. Thanks for presentation. One question though. What's the industry sector or the kind of the area that you receive most demand from right now?
So it's there are many people that asking for our software, but the foremost thing is the automotive, and the reason is that automotive industry is one of the most automated ones, right? If you go to a production line of automotive manufacturer like Volkswagen or BMW or maybe others, even Tesla did that, you will find so many robots. But yeah, and the tasks in those in the automotive industry are also very manifold. For instance, it's different to semiconductors, which are also quite automated, but they have they typically do machine tending things which are not so interesting for us because the robot is not controlled by the same manner that we do, where you have to teach very difficult motions, right? For instance, in the gluing application, you have a bended piece, apply glue on it, right? And that's very difficult because the working piece might be, for instance, not straight and so on. And then the application gets is a perfect fit with our software and our hardware. So this is mostly coming from the automotive industry, but still we are looking at many other things for welding and so on and other industries. Yeah.
Cool. Maybe Georg, if you unshare your presentation, then we can see the questions that also came. I'm sharing my screen here. So there's one question from Fabian. Thanks for joining again. A question, please. Which further advancements do you see on human-machine robots interaction in the next 3 years? And thanks for the interesting talk. Oh no, Georg just unshared himself completely. Please come back. Yes.
We lost Georg.
Well, he's coming back in a second. There he is.
Sorry, I pressed the wrong button. Okay. Yeah. From my observation, the human-machine interaction in industrial applications is currently on pause a bit. I see more advancements really in humanoid robotics because in industry people are still very afraid of the safety topics, right? If you look at the applications that you have, the people are mostly getting the peoples out of the factories instead of involving them with robots. So that third pillar that I had on that one slide might fit much more with domestic robots or robots outside of a factory. And this is the thing that we of course also look at, but because our software can of course do any kinematic, which is the vehicle to get to any robot, right? I see I don't know. I think robots will show up more in public spaces than in industry that can interact directly with human beings. Right. That's my impression currently.
Cool. And then the second one, and then I think we're going to go to the next one here is, would it be possible to have dynamic setup in the produced robot code? The produced robot code is evaluated after a few actual runs and then the process continuously improves.
Yes, this is of course a considerable idea. Basically, I would imagine or interpret it as follows. You basically generate code. The code is running on the machine, you observe it, and then you must check for any errors. Maybe the user tells the software himself that at a certain point the robot doesn't move correctly, or he even manipulates the code that was generated on the machine, and this is then fed back to the software stack that generated the code, so you can learn from those differences, right? And this is of course an idea that you can follow up to. And we have, for the machines that our customers installed, we are able at least and do this sometimes depending on the customer's wishes, that we collect the data in a time series database and then look at it in order to learn how the robot is really used, not only based on generate code, but also on maybe further manipulations that we don't see in our software anymore.
Cool.